Welcome to Unit 8, Notes A, Part 2. Now we're going to look at acid and base properties. In Part 1 of the notes, we talked about a lot of different theories for acids and bases and what can make different things act differently in terms of being an acid or being a base. So we probably should agree on a basic definition that allows certain things to be considered an acid or a base. And if we establish these base rules, then we at least have an idea of what an acidic property or an acidic base might be. So these are the basic definitions. In order to be considered an acid or to have acidic properties, it should be a substance that donates hydrogen ions in solution. In order to be a base or have basic properties, it needs to be able to neutralize an acid. And we'll talk about the neutralization reaction that occurs. It's basically a form of a double replacement reaction where the hydrogen ion from the acid combines with the hydroxide ion from the base and it produces water. This does essentially depend on the Arrhenius definition of a base, which we've talked about is a little bit outdated, and so there are a lot of other things that are to be considered here as well. That could be basically a neutralization or something that decreases the hydrogen ion concentration in a solution. And so those things include metal oxides, hydroxides, ammonia, and any kind of carbonate. It mentions soluble carbonates. Of course, it has to be in solution to have an effect. And then any kind of what they like to call an IB hydrogen carbonate. We usually in the United States call it bicarbonate, the HCO3 minus ion bicarbonate, the bi applying to that hydrogen plus ion attaching to any kind of polyatomic ion, which doesn't completely neutralize and form like a neutral molecule. So when it's still an ion and we add the H plus, we use that bi prefix. So we call that bicarbonate. But IB likes to call it hydrogen carbonate. So hydrogen is kind of their version of our bi prefix, bicarbonate, hydrogen carbonate. Same thing, all good bases. This next definition kind of seems to blend into the note takers, but please superstar it. It's not necessarily new, but newly important. The term alkali not only refers to a basic solution, but like a solution. It has to be soluble. And so that's kind of a new important thing. It has to react with water in order for it to go into solution. And so you'll see with all these examples, we are producing these hydroxide ions as we react different things with water. So to be an alkali, it has to be soluble. Now there are different solubility rules, and I believe I've mentioned before that the solubility rules aren't that important to IB. They only have a few of them that they're really crazy about. In college or for an AP test, you're definitely going to need to know a lot more of your solubility rules. But for IB, there's only the specific ones that are covered that they care about. One way or the other, though, you still need to know that in order to be an alkali solution, it has to be a solution. It has to dissolve. And so it can't be considered an alkali if it's insoluble. So we have kind of this like hierarchy again. We have the soluble bases, and then we have the insoluble bases. Speaking of things that are soluble, we should probably touch on the things that are ions in solution. Our hydrogen and our hydroxide ions are going to be present in any form of neutralization reaction. And so typically these things will combine and they'll form an equilibrium with water. And so this is the basic net ionic equation. Remember, net ionic means like basically what's coming out. And so anything that is aqueous would kind of be an ion still in solution. And so that's why the salt particles, for example, any kind of metal or non-metal involved in the neutralization reactions, they're likely to still be ions, assuming they're soluble in solution, and it's the liquid water that's kind of coming out of solution. Now, of course, we wouldn't call this a precipitate because it's still liquid, but it is a substance that wouldn't cancel out in a net ionic equation. So for your basic neutralization, you're essentially combining your hydrogen and your hydroxide to form water. On to the fun stuff. So we've talked about indicators, specific ones before. Let's first focus in on the two that you, I hope, are familiar with. Probably from middle school, you've heard of litmus paper, which is red as acidic and blue as basic. And then from our titration lab in honors, you've experienced phenolphthalein and the glorious joys of trying to find that perfect translucent pink, that very, very barely pink solution. So those are things that are pretty much one or the other. There's an acid or a base. Sometimes we may need to use a combination of indicators to really narrow in on the pH. Let's say, for example, we use a methyl red indicator and it turns yellow, but then we use a methyl orange indicator and it turns red. Well, essentially we've identified that pH is somewhere between 4 and 5. So we kind of combine indicators to get a little bit more precise in our pH indicatoring, like being able to indicate. It's easy to think about chemicals as just being there to do their job and not think about where they came from. Indicators do have to come from something. All chemicals do. So yes, there are more precise indicators. Something we're going to build up to here in a second is a universal indicator. But there's no like magic universal indicator plant. When we look at indicators, they have to come from something. A common one is a red cabbage indicator, or here you see flower petals or berries can be used to be indicators. And they naturally turn certain colors, just like how iodine turns purple in the presence of starch. So these are natural chemical reactions that form certain products of certain colors. So going back to your probably first indicator you've ever heard of, the litmus paper, it is actually a dye that comes from a plant, a lichen plant. And so that's going to be able to turn red or blue so you can tell acid or base, but it doesn't tell you the specific of the pH. So think about all the indicators we mentioned a minute ago. You can create a solution that contains multiple indicators. And so what we've developed over time is what's known as the universal indicator. And this is the one that was in the buffer demonstration with that little tornado in Honors Chem. It allows us to identify more specifically what the pH is with this kind of general range. And yes, we still see reds as acids and blues as bases, but it's more of a rainbow coloring with more noticeable difference from one number to the next. So these are some of the most infamous indicator. We're familiar with litmus paper. We usually say red and blue. I guess maybe it's a little bit more pink. IB calls it pink, whatever. Methyl orange is one we haven't really ever used as far as I know in honors or anything, but it's one of the more common ones in the industry because it's a very vivid red versus yellow coloring, and it's a little shifted from the neutral position. And then we have phenolphthalein, which of course you know very well from your titration lab, is colorless in an acid and pink in an alkali solution or basic solution. I will kind of comment that phenolphthalein can get a little orangey, and you would think that's a pinkish thing. It's actually an indication of a super strong super strong acid. So if you have like a crazy acidic solution, it will get a little bit orangey and not really colorless. But most things, and we'll talk about this later, are weak acids. Way more common to have a weak acid than a strong acid. So typically we say phenolphthalein is colorless in an acid. Alright, next we're going to look at some neutralization reactions. And you know IB likes you to know there are certain categories of reactions or types of reactions. So these are the basic ones you need to know. The first one is our most common. We used to call this the Arrhenius neutralization. You take an acid and a base, using your strong acid, your strong base. You have hydrogen, you have hydroxide, and you're going to form a salt and a water. You're going to see this with a lot of these reactions. Essentially, we're dealing with double replacement reactions. Hydrogen and hydroxide, and then sodium and chloride. So with the double replacement reaction, you form a salt and ionic compound, regardless of what the cation and anion are, and then water from the hydrogen hydroxide. So that's our basic neutralization reaction, the one we know from honors. But there are more. For this next reaction, we're going to react an acid with a metal oxide base. So metal oxide, some kind of metal with an oxygen, and that's the base. Then we're going to react it with an acid. And I talked earlier about how they write it organically, but this is acetic acid. It's this hydrogen that's going to be donated. And so the hydrogen's going to bond with the oxygen, and you're going to get the copper and the acetate. And so here we have copper acetate and water. So this reaction is essentially a neutralization reaction because it is still forming a salt, a metal and non-metal compound with water. This next one is easy to think about in terms of double replacement reactions, but it's a little weird to think about in terms of neutralization reaction. We are starting with a nitric acid. So this acid is going to donate its hydrogen, and that'll bond with the hydroxide to form water. And so then on the inside we have the nitrate and the ammonium, and so we form ammonium nitrate. So we are still forming salt and a water. The reactants had an acid in it and the products don't. So that makes it neutralization. Next, we essentially have a single replacement reaction where zinc is supposed to be replacing the hydrogen. This is where acids get known as corrosive. So they're able to dissolve basically the zinc and bring it into solution and release that hydrogen gas. This is very similar to what happened in the magnesium reaction when you did that with the eudiometer, the big long gas tube, and collected hydrogen gas in Unit 7 of Honors. So with this, it's really not fitting our traditional definition. Yes, we're forming a salt, but not water. And that's because there's no hydroxide. So how are we going to get water without the O? That doesn't really make sense. And so to get the products on this stuff, we have to think about single replacement reactions. The zinc is replacing the hydrogen, and so you form this zinc chloride, and then you kick out the hydrogen. And hydrogen is diatomic, so it'll naturally be H2, and then you balance from there. Notice the 2 in front of the HCl. So that's how you're getting your balanced equation here. In the second example, we have magnesium trying to replace hydrogen. Remember our weird old acidic acid. So the magnesium's trying to replace the hydrogen. It can, and so we form magnesium acetate and kick out the hydrogen. One thing that these notes don't say in writing, but I think is really important to mention, is that you do have to have the metal, the zinc and the magnesium in this case, that's higher on the activity series than the hydrogen in order for this reaction to happen. So things that are lower, like silver, for example, or copper, those things won't react. You will not get this reaction. You will not get this neutralization if it's lower on the activity series. So this is a single replacement reaction. Remember that. This last reaction is probably the most complicated. It's kind of a double replacement reaction. Let's just look at the first one. You got your hydrogen that would bond with the carbonate, and then separate from that, you have the chloride that would bond with the calcium. And so that salt part still works. The acidic part is a little more complicated because when you form that HCO3, that bicarbonate tends to break up. So whenever you have, let me just jump down to the second one, the carbonate and the hydrogen bonding together, or in the third one, that hydrogen, that carbonate, it always forms H2O and CO2. So that HCO3 minus will break down into H2O and CO2. And then your other substance, these guys, will come from that inside pairing, the sodium and the sulfate, forming Na2SO4, or the potassium and the acetate, forming potassium acetate. So you form the salt still, but then that bicarbonate, or what IB likes to call hydrogen carbonates, will break down into water and carbon dioxide. So that's kind of new too. Bicarbonate breaks into water and carbon dioxide. Let's move on to some vocabulary. So this was something that I really screamed about in Honors Chem. It is very common to mix up the words strong and concentrated. I don't know why you would mix up the word corrosive, but apparently they think you might. A strong acid does not necessarily mean a concentrated acid. You can have a weak acid that barely breaks the bond between the hydrogen and the anion, and so it would not have a significantly acidic pH. But if it's a strong acid, it completely dissociates into ions. Completely separate topic. You could have a concentrated acid, and that means that there is a large number of solute in solution. Separate definition, in my opinion, completely. A corrosive acid, they say, is chemically reactive. To break that back down, think back to our last example where we had the single replacement reactions, like the zinc or the magnesium, being taken into solution because they're higher than hydrogen on the activity series. That's really what it comes down to, is that they go into solution because they're able to replace hydrogen on the activity series. So, of course, if strong and concentrated are not synonyms, of course, weak and dilute are not synonyms either. A weak acid or base would just have a very slight dissociation into ions, having more of a covalent character, and then a dilute solution would mean that there's very little solute in solution. There's completely different definitions. So in a strong acid, perfect example, hydrochloric acid, the hydrogen and chlorine ion completely break apart. The chlorine takes both electrons. The hydrogen is completely deficit electrons, and so we have the hydrochloric acid breaking down into hydrogen ions and chlorine ions. On the flip side, if you take a weak acid, like acetic acid, yes, some of the hydrogen does dissociate, and you get hydrogen versus acetate, but there is some reverse reaction where we're going back to that covalent compound. So we call this partial dissociation. Really big deal, whether it completely dissociates or partially dissociates. The exact same concept applies in the exact same way for a base. If it's a strong base, it's a one-way complete reaction. If it's a weak base, it goes both ways. There is some reverse reaction. So just as a general statement, strong acids and bases completely dissociate. Weak acids and bases partially dissociate. This partial dissociation is going to be something that we start to account for in our calculations. It's not something we dealt with in Honors Chem. But from Honors Chem, I started trying to encourage you to kind of remember what are strong acids and bases. I offered extra credit to memorize them. That's because there are certain assumptions you can make with them that are going to make these calculations easier. But most often, you're going to be dealing with a weak acid and base because they are so much more common. There are only 6 strong acids and bases and only a few strong bases too. So here we have a table of the strong and weak acids and bases that you should know. The strong acids are the ones I was just talking about that I've really put memorizing from the beginning. We have sulfuric acid, nitric acid, and perchloric acid with the polyatomic ions, and then straight down the middle of the halogens, hydrochloric acid, hydrobromic acid, and hydroiodic acid. And yes, it is perchloric, DClO4. ClO3 actually has a dissociation of about 98%, I think, something like that. So it's pretty strong, but these are the guys that are like 100% dissociation. Sulfuric acid has a little asterisk there we'll talk about on another slide because it has 2 hydrogen ions. As far as the strong bases go, we have talked about how anything in group 1 or group 2 with hydroxide would act as a strong base. And that's because most of the ones in group 2 have very high dissociation rates. But according to IB, as we like to say, it's these 4 in particular that are the strongest, or that have no exceptions to a 100% dissociation rate. And so the ones you need to know for them are lithium hydroxide, sodium hydroxide, potassium hydroxide, and barium hydroxide. The difference between what we talked about in honors versus these 4 is kind of a solubility issue and how much is actually going to dissociate under certain conditions. There are exceptions and things like that. So they are right in a sense. These are the 4 that there's no limitations, no exceptions, no problems. These guys will always 100% dissociate. So these are the 4 they would like you to know. So here's where I kind of disagree with IB a little bit. Weak acids and bases, in my opinion, would be anything that does not 100% dissociate. That's what a lot of your universities are going to say. But there are some notable ones that are particularly bad at dissociating, and so I think that's what they're going for here. these guys that are very, very terrible at dissociation, and you're going to have very low percentages. Like some of them are like 5% dissociated. So they have very high covalent character, very low dissociation. And so for the acids, we have ethanoic acid, carbonic acid, and phosphoric acid. And for the bases, we have ethylamine and ammonia. So these are the things you're supposed to know about which things particularly are good at dissociating or particularly bad at dissociating. So here's our little footnote about sulfuric acid. I mentioned it was because it had 2 hydrogens. So there's a term here I'm not sure if you've heard of before, diprotic. Protic refers to the proton of the hydrogen. So typically acids are monoprotic because they have the hydrogen as a 1 proton. But when it bonds to things like sulfate or phosphate, might be triprotic, things that have more hydrogens, that increases the number of protons. And that complicates the mechanism. IB doesn't want to get into that. It is complicated. And so we won't be talking about anything to do with the sulfuric acid. You should know it's a strong acid, but all of the strong acid examples IB uses will use the other 5. And that's because of its diprotic nature. The last thing that we want to talk about today is, say you're given a solution and you don't know if it's a strong acid or a weak acid. Like, how are we supposed to tell the difference between strong and weak? And it really doesn't matter if it's an acid or a base. This is really going to only tell you if it's strong or weak. You would have to determine acid or base by a indicator of some sort. But is it strong or is it weak comes down to, does it dissociate well or not? And the dissociation is going to influence these 3 things. So if I have a strong acid or base, I have a high level of dissociation, which is going to put more ions in solution. And so if I have more ions, I have higher conductivity. So a strong acid or base is going to be a better conductor. No difference whether it's a strong acid or a strong base. Either one would have more ions in solution and be a better conductor. With more ions in solution, you have more particles in solution. And so that higher concentration is going to increase the rate of the reaction. Think about collision theory. More particles in solution are more likely to bump into each other, and that's going to increase the rate. The last thing can get a little bit complicated, and that's because the hydrogen concentration is inversely proportional to the pH. So if you have a high hydrogen concentration, you have a low pH. But the degree of dissociation still affects this, because the higher the concentration, the lower the pH, and vice versa. And so basically we can simplify this for now, that the greater the dissociation, the more effect on the pH. And in our next notes, which will be Unit 8 Notes B, we'll talk specifically about pH and pOH and how those things can be calculated based on concentration. So we'll see you there.